So where do we leave off? Let's review. I threw a lot of tactics at you yesterday. Let's review some tactics. Let's review some tactics before we get to the homework. What things we know about obtain. When would you use obtain? When would you use the tactic obtain? To get something, if you know that something what? Yes, exactly right. If you have a hypothesis, what should we call the hypothesis? H. H is a hypothesis that there, oh, this isn't going to work, so let me grab an exists. If you know that there exists something, a thing, with some property, then you can say obtain, then you can say obtain, and then I need my little curly brackets. Give me a curly, here we are, a curly bracket and an end curly bracket. We can obtain that thing and the prop, the hypothesis, whatever we want to call it, H prop or something, out of capital H, right? Remember obtain? We can say this, and we will get the thing and the property, the thing and the property. Okay, what else did we learn? We learned have. Have is when would you use have? Yeah, you could use have for anything. If you want to just make you want to declare a statement. If you want to claim that something is true, haves can come out of thin air. I want to claim that the earth is round. Let's have, for example, have, we can give that have a name, fact one or something. And then what does fact one say? It says, is round of earth. And then I have to give you a proof and then if I can't give you the proof right now, I want to delay the proof. Sorry. Okay. So that's what this would look like. Something like that. Yeah. I'm learning how to use this stuff. Okay. That looks good. When would you use have? If you want to just make a claim, you can give it a name. If you don't give it a name, if we didn't name it fact one, its default name would be this. Okay. Great. What other tactics did we learn? Use. Okay, beautiful. When could you use? Yeah, if the goal is there exists. Let's say you have a hypothesis H. Well, let's say you have H of type, let's say you have a Jiven of type person. There's a person named Jiven, and the claim, the goal, and let's say you have anyway, and you're trying to figure out if somebody's in the room. And the goal, where's that goal symbol? Let me grab the goal symbol. And the goal is to prove that there exists a person in the room. So the goal would say there exists, let me grab this exists sign, there exists somebody of type person such that is in room somebody, right? Let's say that's your goal. Your goal is to show that there exists somebody of type person so that somebody is in the room. Then if you apply the tactic, if you write use Jiven, then the goal will change to what? Instead of there exists somebody who's in the room, now we have to prove. We're saying Jiben is the person in the room. Exactly. So we're saying not that there exists somebody, but that is in the room Jiben. Does that make sense? Everybody following how use works? Navia, you look sad. Did we have used Navia in the room? Does this make sense? You sure? Okay, let's try another one. So, so again, if you have a hypothesis, if you have a there exists in a hypothesis, then you want to obtain that thing. If you have a there exists in the goal, then you want to use that person, place, or thing. Okay. We saw unfold. When would you use unfold? When would you use unfold? Somebody new? Khalil?
And you want to find out like the steps for how you need to prove the goal. So like if it says like the goal is this, you need unfold would tell you, oh well, that means you need to prove this, and you need to prove this, and you need to prove this.
Exactly right. So unfold reminds you what the definition of something is. Unfold, if you don't remember what it means to be wearing jeans instead of shorts or something, is wearing jeans. So maybe your goal, say your goal was, who am I going to pick on? I said I'd pick on Nadia. Is wearing jeans. Are you wearing jeans? No. Okay, so the answer would be no. Is wearing jeans Navia? Okay, if you don't remember what is wearing jeans means, and there was a definition, and there was a definition, let's say the definition was is wearing jeans. Let me make this a slightly longer one. Definition is wearing jeans of a person, of anybody, somebody of type person, is a true or false statement. And you're wearing jeans if you're wearing long pants, and those long pants are made out of jeans, out of jean material, right? Denim, thank you. Thank you. If two things, is wearing long pants somebody, and where's my and symbol? And pants are denim. Pants are denim, somebody. Okay, so that's what it means to be is wearing jeans. Let's say you had this definition, but that definition is not fresh in your mind. The definition is wearing jeans is you're wearing long pants, and the pants are denim of, right, of this person. And you want to prove that Navia is wearing jeans, but you don't remember what that means. So in this, if at this point you write unfold is wearing jeans, then the goal will become, what will the goal become? So everybody take 30 seconds and write on your paper what the goal will become. Instead of is wearing jeans Nadia, the new goal will be what? Yes. Yes. The quiz for tomorrow is how well do you understand these tactics, and
You have to write this over.
well, I'll just say this is a perfect question. Yeah. So this is a perfect question for the quiz tomorrow. Suppose you know that is wearing jeans of somebody who's a person is a true or false statement, and it contains two other true or false statements. One is that somebody wearing long pants, and two, well, are the pants that person is wearing made out of denim? And then I say, what would happen after unfold is wearing jeans if your goal was is Navi wearing jeans? What would that turn into? So take 30 seconds and write it down. Give me a thumbs up if you are pretty confident in your answer. Okay, a couple of thumbs up, a couple of thumbs down. So Avi, can I pick on you? That's the nice thing about giving me the thumbs down, is that I can pick on you. Okay. So this is the definition. All this definition is doing is wrapping two other facts into one. Instead of everywhere having to say, you have to wear long pants and those pants have to be made out of denim, now I can just say one thing, you're wearing jeans. Yeah. So if we're trying to prove that Navi is wearing jeans, and I say unfold the definition of what is wearing jeans actually means, what will the new goal become?
Is Nadia wearing the long pants? Is it, and is that then?
Exactly right. Exactly right. These two things with somebody replaced by Navia are what we're going to have to prove. Okay, does that make sense?
Wait, what's the upside? Like the carrot?
The carrot thing means
And?
yeah. So let's those are tactics. The sideways T. This sideways T means goal. Yeah, let's do a little vocabulary also. I guess this isn't vocabulary, but I don't know. What's the word? Syntax. Okay. So this sideways T, syntax. Okay, sideways T. Oops. Sideways T means goal. This caret means and. Any other syntax I need to cover? There exists, okay, there exists and for all. Those are mathematical, I guess these are, is there exists. This is good. You guys are writing my quiz for me. Now I know what to ask you. It's for all. Okay. The colon and the colon equals, right. So this is a general pattern that yeah, so that it's like have or definition or theorem. So we might have or maybe definition or maybe theorem, and then name, the name for that thing, you give it a name. And then colon is what you want to say, then colon equals, and then a proof that it's true. Proof that it's true. Okay, does that make sense? That's just what it looks like. Jim. Okay. Okay, so this is a little slight. There are two ways to prove that something is true. If you know the proof already, if you have constructed the proof term, if you know the proof already, you don't need to say by, you just give the proof. But if you have to build up the proof, using a bunch of different facts, then start the proof with by. So let me show you examples of that. This step one, did we need to use a lot of facts in order to build up step one? Or did we just call cert of points A, B? Yeah, we just called it, so you don't need to say by. It's a one line. As opposed to this step three, where we're gonna have to argue. And so, well, we haven't said what it is. The proof is just sorry right now, but we're gonna have to put in a proof here. So it's like its own little theorem inside of this theorem. And here, by the way, we also have a by when we prove the theorem. Jivan and then Sami.
Why does the computer know that difference? Why is that necessary?
That's how the computer knows whether the next thing you're about to write is exactly the term that it's looking for, or if it should go into tactic mode. And like in the proof of step one,
The equivalent of writing brackets or something in Java.
it's like brackets. You can think of it as brackets. Yeah. Ideally, they would figure out a way to do it so that you don't have to distinguish between the two. There's a technical reason why that's how it's done. Something.
So like the library 7 since circle point is already defined,
Yes.
you like just need to name it, not like actually like put in the proof and stuff.
Whoa, so line 36 says we're gonna make a new fact. We're gonna call it step 2. The fact will say that there exists a circle beta, so that yada yada. And then the proof of it is this one fact, circ of points BA. And circ of points BA is exactly this.
Yeah, because already defined.
It's already defined. As opposed to, let's see, do we have something that we took a little time to prove? No, we don't. Well, actually, when we're here, okay, this is slightly different because we use the constructor to break up why something's true. It's really, this is the first by that we saw, which breaks up the, goes into tactic mode to prove this theorem. And then here, step 3, this step that Euclid missed, we're gonna have to provide a proof there. Okay, so we're gonna go into the proof of this. So far, so good. Now, this is a really good place to remember another tactic. There was a tactic called, how would we, if we have 2 things to prove, how would we separate them into separate goals? And we're gonna like construct them separately and then put them back together. It's called constructor. When would you write constructor if your goal is to prove 2 things, then writing constructor gives you 2 different goals. If we looking at exactly the previous line, for the previous line, constructor would result in what? Oops. There we go. Other than Sanvi, other than Khalil. Sanjana, can I pick on you? What would happen if you did constructor to this pair of things? What was that?
I don't know.
Okay, so this is an and, so we have to prove both that Navi is wearing long pants and that the pants that Navi is wearing are made out of denim, even though we're not gonna be able to prove that because it's not true. But that's okay, that's still what that's what the goal state is. So if we say constructor, that says break these into 2 separate goals. So what will the first goal be? Exactly, and what will the second goal be? Exactly right. Okay. And when we have multiple goals, when we are in a situation where there are multiple goals, how do we focus in on just the one goal at a time? Sayuri. Okay, you can write sorry. Sorry says, I don't want to deal with this. Like if we're here we have 2 goals exactly after this constructor step. On the previous line, we have to prove that the distance from A to B is equal to distance to B to C, and distance from A to B is equal to distance from A to C. We hit it with constructor. Now we have 2 goals. One is distance AB is equal to distance BC. There's a second goal down here. This distance AB is equal to AC. It's true that I can say sorry and just ignore the fact that I have to prove the first thing. That'll make the computer say, okay, now prove the second thing. Sanvi.
Is it backslash dot?
Exactly. It's this backslash dot, backslash dot, and I guess a space, will tell the computer, so it looks like this. Will tell the computer to not show the other goals. So what's the backslash? I just literally mean like backslash and then dot and then space, and that'll make that kind of a dot. Yeah. So if you type backslash, then dot, then space, then you'll get something that looks like this. And that'll tell the computer. So right here, the only difference between here, okay, I'm at the end of the constructor line. I have 2 goals. If I go to the very next line, I only have one goal. The second goal disappeared. Okay. So we like zoom in on a goal. Two more tactics that we learned about. Oh, Abhi.
Why do you separate the goals?
Okay, so at the end of when we unfolded the definition of an equilateral triangle, we have two things to prove. And you can try to prove both of them simultaneously, but it's a little bit more complicated. So let's make our life easier by constructing a proof by breaking the one goal with two parts into two goals with one part of each. So that's what constructors do. Constructors breaking those two bits into, well, there's still two bits. We can't get away from the fact that we have to prove two facts, but we can work on them one at a time. Similar.
So, first, you have to not write sorry, but
Well, once we've proved the first goal, and the first goal is done, now we get to work on proving the second goal. And once we prove the second goal, there's no more sorries. The whole thing is, well, you don't have to write the sorry. If you don't write the sorry, it's going to give you an error message that says, hey, you didn't finish the proof. Like, I know, I didn't finish the proof. Sorry, just don't give me an error message, please. So sorry just tells the computer, don't give me an error message. You don't have to write it. You can just live with an error message. It'll say, hey, you didn't, what's happening here? No, it's okay. Don't worry about it. We'll get to it. Does that make sense? Okay.
Whatever guy makes the home.
So I put one backslash dot to zoom in on the first goal and a second backslash dot to zoom in on the second goal. So this is just for me to be able to easily see once I have a constructor, that means I have two goals. This is the work to finish the first one. This is the work to finish the second one. It's not strictly necessary. In other words, if you just do this, it'll work just fine. But now I can't tell if there's like 5 lines to solve the first one and 10 more lines to solve the second one, my eyes don't immediately know what's going on. Am I still working on the first goal? Is it done already? What's happening? So that's the beauty of this way of organizing things is here I'm working on that first goal. Now I'm going to work on the second goal.
Can you go to the homework line real quick?
The homework line? Yep.
Yeah. Also, it's still. So if you didn't have the dots, it would always tell you there's two goals, but because you have the dots, it tells you one goal.
Well, okay.
So
So let's see what it's going to do here. So we did constructor, so now I have two goals. Now I do convert. It's working on this first goal. It's leaving the second goal alone. It's still there, but it's not doing anything to the second goal. Then I do exact. The first goal is done. There's still a goal left. It just automatically says, okay, first one's done. Let's slide the second one up to the top. Now you're working on the second one. So you can work on them in this way without specifying.
it's just for organization.
It's just for organization. This is just for organization. It's not something that the computer needs. It's something that's good for us. In fact, this unfold equilateral triangle is also just for us. The computer knows the definition. The computer doesn't forget the definition. We forgot the definition. If I comment out the unfolding, it still knows that is equilateral triangle means two different things. And so when I do constructor, it says, okay, I've broken it into those two different things. It can skip the step of, hey, can you remind me what the definition is?
The unfold, it reminds you where.
It only reminds me so that I see what equilateral triangle means. It means these two different things. It reminds me in the goal state.
Okay.
But the computer doesn't need that reminder. It knows the definition. Simon.
So what if you wanna like split apart 3 different goals? Would you still use constructor?
Yeah, so 3 different goals. If you have 3 different goals, you have like P and Q and R. Secretly, there's no such thing as 3 different goals. It means P and Q and R.
Okay.
And so if that's your goal, then the first constructor will give you P and Q and R. And then you work on your first goal.
Okay,
And then we're done with this goal. What are you going to do?
just split it.
Just do constructor again. Yeah, and then you'll have Q and R separately.
Yeah, cause we're gonna have 3 goals, right? The last pair lines. Or is it just like,
You mean when we're working on have 3, we're gonna have 3 goals?
do we have to prove like 3 sets of like equals in order to prove that's an equilateral triangle?
The way we set up equilateral triangle, so it depends on us. The way we set up an equilateral triangle is just with 2 things. We said we will consider 3 points to determine an equilateral triangle if the distance from A to B is BC and the distance from A to B is AC.
Oh, so
And that's all. If you want, we can add more to the definition and then we'll need another constructor. Do you want to add more to the definition or? You guys are looking at Sammy like you better say no because we don't want to do more work than we have. I'm okay with this as a definition. You're absolutely right, though, that in Euclid, we did take the third step to say, well, if this is equal to that and that's equal to that, then BC and AC are also okay.
So it's because we just set the definition to.
We set the definition to just two things. Not it.
What does it?
What does constructor do? So it's exactly what we discussed here. If you have a goal with an and in it, then constructor creates two goals, but each of the goals is simpler. So I have a complicated goal, but only one goal. I have to prove both of these things. Constructor says, okay, I'll figure out how to put them back together for you if you can prove them to me one at a time. Does that make sense? Everybody with me? Anybody against me? Okay. So we had two more. This is all still review. We learned a lot last time. We had two more things. We had convert and exact. So when would I use convert? When would you write convert? Do you have a question or you want to tell us the answer? I want to see if someone else knows the answer too. Siri. Yeah, convert is a really powerful tactic. It can do all kinds of things. Let's say you're trying to prove, that, I don't know, give me something that you might want to prove. Say you have a hypothesis H, you know that let's just say x plus y is equal to z plus w. Okay, and then what you're trying to do is you're trying to prove that a plus b is equal to z plus w. A plus b is equal to z plus w. Okay, so suppose you're trying to prove that a plus b is equal to z plus w, but what you know is that x plus y is equal to z plus w. What will happen if I say convert? What will happen if I write convert H? Other than Jivan, other than Khalil, other than Sandvi? Other than Sayuri? I picked on you already, Avi, but you know the answer? You think you might know?
Wait, is it like the triangle thing? So the.
Well, what convert does is
It says what's the right of it? Equals Z plus.
the triangle. Oh, I'm sorry.
Like,
I'm confused.
I guess it's. Huh? Oh, wait.
H is just a hypothesis. Suppose we already know that x plus y is equal to z plus w.
Oh, wait.
And what we're trying to prove, our goal is to prove that a plus b is equal to z plus w.
X plus Y.
Yeah.
Say it again. I'm gonna pick on you, Akshay.
X plus Y is equals B.
So if we, okay, so this is really, what convert is gonna try to do is pattern match. And if you just leave it as is, if you don't restrict the convert, it will turn the goal into a pair of goals, The pair of goals will be exactly. It'll be, okay, I think what you mean is x is equal to A and y is equal to B. Because if you can prove that x is equal to A and y is equal to B, then H is what you wanted. But maybe it's not true that x equals A and y equals B. Maybe it's only true that x plus y is equal to A plus B. So converted down to too many levels. Exactly. So maybe it's not true. It's not true that x equals a, etc. So we don't want to convert this far. To restrict it, we say convert h using 1, or maybe using 2, or maybe using 3. Using restricts it to how many levels of conversion it does. Then the computer will respond. Then the response will be it notices there will only be one goal, and the one goal will be x plus y is equal to a plus b. Or maybe a plus b equals x plus y, I'm not sure. Or maybe a plus b is equal to x plus y. I don't know in what order it'll make that plus. Okay, does that make sense? So it's trying to match this pattern, and if you just let it go, it's going to match it to the smallest detail that it can. And if you want to stop it, say stop it at level 1. Okay, I see that there's an equal sign. Z and W match perfectly. So why are these two things? You can prove to me that those two things are the same. Then I can cascade everything back up. Bye-bye.
Basically, like abstract is gonna like give us an idea of what you need to do so that you satisfy your goal.
Yes. That's it. Avi, then Jevin, then Simino.
Wait, how many levels are there? Is it just, it's like,
If you have a very complicated expression, if you have f of g of x plus y of h of whatever, and on the other side you have f of, I mean, there's, when you create an expression, like if I create an expression, anyway, let me not write anything. When we create an expression, actually it's almost always some binary thing, like x plus y, and then I'm going to multiply that by z, and then I'll square that, and that's another operation. So those operations are secretly all nested in the same way that this is nested. And so in every nesting, convert goes one level deeper. And so here there's a nesting. First of all, there's an equality. The next level, there's addition. So if it just goes to level 1, then it says is the left-hand side of the goal equal to the left-hand side of that. If it goes one step further, I see that there's addition on both things. And so maybe the terms themselves are equal. So there's no a priori bound on how far you might have to convert. Jevin and then Simino.
Is it additionality where x is y equal to x plus y equals a plus b, but a plus b doesn't y plus y? Is that ever a thing?
Is there a geometry where x plus y is equal to a plus b, but a plus b is not equal to x plus y? No, because the equal sign. So this is something you needed for your homework, and I know some of you Googled around to figure out how to do this, but what I didn't tell you is how to symmetrize the equal sign. Just like we can symmetrize inside distance, we added that as an axiom because distance is something that we don't have control over. But the equal sign can be symmetrized. And note that if, let's say it like this. Note that if you have a hypothesis H, which says that P is, let's say X is equal to Y, then if I say H dot sim, that will be the hypothesis that Y is equal to X. Okay, if you have a fact that X is equal to Y, then the equal sign by the definition of the equal sign satisfies this symmetry. So you can flip it around the other side.
So for our code, it would be called distance, which is the same thing this way.
So our code has another axiom, which is about distsim. Distsim is not something that's built into Lean, because dist isn't built into Lean. We created this thing called dist that takes two points and gives a real number. It does not know a priori. So distsim is something that only works on the distance function. It does not work on the equal sign.
Oh, this works.
This is like equal sign sim,
Oh,
which is built into Lean.
oh, okay. For the one we made, we works for points.
The one we made only works for points. Yeah, and points don't points we made up the word point. Okay, does that make sense? Similar.
In here, that's not necessarily the case.
It doesn't know. All it says is, it wants to try to help you prove what you're trying to prove. and you say, look, I already proved that x plus y equals z plus w, and I'm trying to convert that into the goal, the thing that I'm actually trying to prove, which is a plus b is equal to z plus w. Can you help me? And says, oh, sure. If you can prove that x is a and y is b, you're done. And like, no, actually, that's not true. I can't prove it because it's not true. What I can prove and what is true is that x plus y is equal to a plus b. Could you stop one level higher? It's trying to be very helpful, and it's sometimes too helpful. It's saying, if it were the case that x was a and y was b, then I can prove the rest of the point. Like, but that's not the case. Only this is the case, and could you reduce the problem to this? Okay, does that make sense? And that was, any more questions? That was convert, and lastly, that should have been maybe the first thing that we talked about, is exact. When would you write exact? Other than Jimin? Other than Sami? Okay, Santosh? Yeah, you just say what Jimin said. Yeah, if your goal is, should I grab a goal? Is wearing long pants Navia? Are you wearing long pants, Navia? Oh, we have a we know that Navia is wearing long pants. Oops. Here we are. You are wearing long pants. Okay. So if we know that Navia is wearing long pants and we're trying to prove that Navia is wearing long pants, then what we're trying to prove is exactly what we already have. If your goal state is this, then writing exact H will result in we're done. No goals. No goals left. No goals. Okay, you're done. Okay, does that make sense? Fine.
So suppose if wearing long pants Navia is false,
Mhm.
what would the computer like say in return to that? Like it's false.
You mean, let me try to write your question. Suppose instead we can prove that it's false. Suppose instead we have, where's my not? Not, thank you, not symbol. Suppose instead, suppose instead we know that Navia is not wearing long pants, and we're trying to prove that Navia is wearing long pants. Is that your question?
Yeah.
We're in deep doo-doo if that's the case.
So like, yeah, what would the computer respond to that?
Oh, well, if we said exact H?
No, like suppose, we have is wearing long pants Navia, and
Yes.
then prop, but then the answer is false. Like, so how would the computer like respond to that?
Suppose we know that Navia is wearing long pants.
No, like
No.
she's not wearing.
She's not, suppose we know that she's not wearing long pants, and what are we trying to prove?
That, no, but I'm trying to no, like my question is that she's not wearing long pants, but our goal is wearing long pants. How
Okay.
would the computer respond to that?
So the computer is not going to respond to it at all. It's just going to keep waiting for you to give a proof. But you're going to have a very hard time proving that she is wearing long pants if you know that she's not wearing long pants. There's no tactic that lets you solve this goal from this hypothesis. It's just not provable because it's not true. Hopefully, Lean cannot prove false statements. There's something called Gödel's theorem that says we will never know if it can or can't. So you're
Could you put steps on how ground proofing is, like she changes stuff like that?
it should not be, okay, so actually it's let's move away from this example because there's a deep discussion here that I really want to have, and I know that I'm going to waste all of our time if I go into it about the law of excluded middle and contradictions and Gödel's theorem, and there's lots of really, really fun stuff that we're on the edge of that I want to run away from. Gödel? Well, it's Gödel. So look up Gödel's incompleteness theorem and inconsistency theorem, completeness theorem. is that we don't know. There's no proof that we can't prove a false statement. Well, yeah, let me just say, this is a very, very long conversation that I would love to have sometime. Yeah, yeah. Bob, you had a question, comment?
How exact? Last step.
You mean here or in this hypothetical? This one. So we assume we've already proved H. We've established H, that Navia is wearing long pants. And our goal is to prove that Navia is wearing long pants. Well, then the thing that we want to prove, we already have. We have exactly the thing we want to prove. So when we write exact H, it'll say, okay, good, your proof's done.
Can you go back to the code?
Go back to the code. So,
Explain the exact series.
okay, so what does dist sim AB mean?
That AB is the same as BA.
That the distance of AB is equal to the distance of BA. What are we trying to prove?
The distance of AB is equal to distance of BA.
So if we can give exactly that, that will end the goal. Okay.
Wait, so the computer doesn't know what that the exact statement that we've proven the goal, we should tell it that this is the final step.
That's right. So for example, I can have a have dist sim AB, and it's complaining that, so let me put sorry so it won't complain. Okay, so now I have a have, which is this, and this is the distance from AB is equal to distance of BA. The computer does not know what to do with that until it's told that this is exactly what we want.
But isn't that what the dist sim does?
So we made a new fact. The computer by itself, before we put that have there, by itself, the computer knows only the things that we've proved so far. So when I say have, let me remind you of the fact that this sim of AB, in other words, this AB is equal to this BA. It says, okay, now I'll grant you this new fact. And how do you want to use this fact?
I just realize that's the final goal.
Correct.
Okay. So you just have to say it's pretty much, by the way, this is the
By
final.
the way, this is the final goal, which is exact. That's exactly what exact. So then exactly this thing says no goals. And then it's complaining that there's a sorry because there aren't any goals to be solved. Okay, does that make sense? This is really great because we're hitting the part where I think we've learned most, if not all, probably not all, but most of the syntax we'll ever need. And now we can actually do math. We're getting close to, I'm not promising that there's not going to be another tactic, but we're getting very close, Avi.
So the exact functions is always like verify.
If you have built up in your hypotheses something that is exactly the thing that you are trying to prove, then exact of that fact, whatever it's called, will just stops. Yeah, there's no goal.
So what if you were to do, what if you had like something that isn't the final goal, but you said exact this, would it think that the theorem is complete?
So let's try. How about exact step 6 or something? It says no. You're saying exact, but step 6 says this BA is equal to this BC. And I'm trying to prove this AB is equal to this BA. They're not exactly the same thing. I don't know what to do with that. Just gives you an error message. Does that make sense?
Yeah.
So now let's do your homework. What was your homework? It was to prove this. It was to prove that distance of AB is equal to distance from A to C. Javen's got it. Cool. Do you want to say something or you want to tell us how you did it? All right, go ahead.
Step 5 dot sim. That was all I did.
Okay, so if we look at step 5 dot sim, step 5, okay, so check this out. Step 5 dot sim is just gonna dot sim, not dist sim. It's not that we need to replace A and C are in the right order, and A and B are also in the right order. The only thing that's not in the right order is the two sides of the equal sign. So step 5 dot sim is exactly the goal.
That's why you don't need the dist.
You don't need this sim. It's not that the A and the B are in the wrong order. The A and the B are in the right order. The A and the C are in the right order. What's not in the right order is which one is on the left side of the
But
equal sign.
if you were to still put the dis sim, nothing would happen, right?
Where do you want to put the dis sim?
Like.
If you put it this sim, it would switch the
Like if
them
it-
around and would get you further away from. like,
Yeah, this sim flips the A and the B, but it doesn't move things to the other side of the equal sign.
Well, does it flip it or just does it state that it's equal?
If,
So dis sim is the fact that dis AB is equal to dis BA. And then you could use like convert or something else to get down to. So let's break this into two steps so that we see it. Let's do a half colon equals step 5 dot sim. So that we see that explicitly. So step 5 is distance from A to C is equal to distance from A to B. If I symmetrize that, I get a new thing, which says distance from A to B is equal to distance from A to C. And how do we close the goal? Exact this. Exact this. And there's no goals. Okay, and you could do that in one step. You don't have to do it in two steps. You could just say exact step 5 dot sim. The step 5 dot sim is the thing that you want.
So is dot sim axiom?
The equality, the symmetry of the equality is an axiom in Lee. Yeah, that's built into Lee. Akshay, then Sam.
There's multiple this statements. How does the computer know which one to refer to?
Yeah, so if I make one this statement and then I make another have that I also don't name, I'll just call this step 5 dot sim for no reason. The old this is dead. It's still there, but it's dead. I can no longer access it. So something's gone wrong that maybe I don't care about that statement. I'll never need to access that statement anymore. And now this is the new this. So you can always create new thises and forget the old ones. Then the old ones are that this is dead to me.
If you use the new this, if you use the new this, can you then access the old this?
No.
Oh, no, it's just permanently
dead.
dead, okay.
Yeah. There is a way to recover dead, to resuscitate dead hypotheses and variable names, but let's not go into that. We should just name them. If we ever need to use them later, we should just name them. We shouldn't have too many business words.
So, why is our goal, like, distance of A, B is equal to distance of B, A, when it's already like, that doesn't prove like our equivalent triangle is equal?
Okay, so how we got there, let me comment out this second half. How we got there was we were trying to prove that distance from AB is equal to distance from BC.
Yeah.
And in step 6, what we know is that distance from BA is equal to distance BC.
Yeah.
Which is very close to the goal, but not exactly.
Oh, so you wanna make A, B, and B, A equal, so we can then just use that.
Well, so that's where we use convert.
Yeah.
So we converted step 6, but if we do the full conversion of step 6, we'll say maybe A is equal to B and B is equal to A.
Yeah,
But that's not true. A and B are two different points.
yeah.
What is true is that the distance from A to B is equal to the distance from B to A.
Oh, so we just use this sim and then let's use.
Well, first we use convert step 6 using 1.
Yeah.
And here's the moment of truth. Does it say dist AB is equal to dist BA or the other way around? I don't know what it's gonna do. Okay, if the dist AB is equal to dist BA.
That's a new goal.
That's our new goal. After the convert, that's our new goal. And then we know that that's the case because of this sim AB.
Wait, this is referring to the have, like before.
Which one? This one?
Yeah, like an exact this is referring to the have, like the. like
Yeah,
the
if I gave this a name, if I call this step 7 or something, then exact step 7.
Oh, it's for sure.
It's just a shorthand. Yeah, if I don't give it a name, this was here, I think. Where was it? Here it is. If we didn't name it fact 1, the default name would be this.
How do you name it?
You just give it, yeah, just put it in front. So this is the syntax. It's whether it's have or definition or theorem, then you give it the name, then you give it the colon. There could also be extra assumptions. For example, when we had this theorem, prop 1, we had the assumptions that someone gave us points A and B. Okay, so it's theorem, then the name of that theorem, prop I.1, then the assumptions, and then what we're trying to prove and then colon equals, and we're gonna prove it by a series of steps. So I need the by.